let's look at the magnitude again, and this time really calculate an actual force. So I'm going to do a problem that I found in the book. It's about something that Richard Feynman said. So Richard Feynman, a very famous physicist, won the Nobel Prize, crazy guy, everybody loves him. So Nobel laureate Richard Feynman once said that if two persons stood at arm's length from each other, and each person had 1% more electrons than protons, the force of repulsion between them would be enough to lift a weight equal to that of the entire Earth. So the point he was trying to make is that electrostatic forces can be very strong. So that was the idea. But let's see if this is correct. Let's see if it's right. So let's see. It was two persons stood at arm's length. Arm's length. So arm's length I think of as our hands are touching, and if your arm is about 3/4 of a meter is what I measured. Let's say the two are 1.5 meters apart. Now, if you ask a physicist to draw a person, that's basically it right there. That would be a person. I'll go a little more detailed on you, because we're trying to make this very friendly and sort of advanced class. So I'll do it like that. There you go. There's two people at arm's length, 1.5 meters apart. Now we also have to make a few assumptions. We have to assume their mass, which can be a little sensitive. So 70 kilograms. We'll say each one is 70 kilograms. And from this, we now know enough to calculate the charge and the force that these two would experience. So let's see, how much charge? Let's do that part first. Now that we've done this a little bit, we might be able to sort of do it all in one step. First of all, it's going to depend on how much they weigh, or what their mass is, I should say, 70 kilograms. And then we're going to divide that by the mass of a nucleon, 1.7 times 10 to the minus 27. And that's in kilograms per nucleon. So that would give you the number of nucleons. But then, only half of those are useful in terms of charge, so it's 2 proton per nucleon. So we're basically just dividing that by 2 to really just get the number of protons. So there's your number of nucleons, and now each one will have a charge of 1.6 times 10 to the minus 19 coulombs. So if you multiplied all that out, you'd get coulombs, right? This would be the charge, the positive charge in a person, just their protons. But then the question he said, or what he said was, imagine that each person just has 1% more electrons than protons. So the excess charge we're building up is 0.01. Taking the total charge in a human, just taking 1% of it and saying that's an excess of electrons, not protons. So I'll slap a negative sign on there. Right? So if you go through all that in your calculator, you'll get minus 3.3 times 10 to the 7 coulombs. Again, that's a lot of charge. And it's comforting that's not that different from the Teflon rod. Right? The Teflon rod had 18 million coulombs. This is 33 million coulombs. But of course, it's a much bigger mass, but then again, it's only 1%. The numbers look about right. So 33 million coulombs is the excess charge. So now, let's calculate the magnitude of the force using Coulomb's law, the magnitude part. So it's 9 times 10 to the 9 Newton meters squared per Coulomb squared, there's KE, times 3.3 minus 3.3 times 10 to the 7 coulombs times minus 3.3 times 10 to the 7 coulombs. So we're assuming the two people are identical. Each one has that charge. So that's Q1 and Q2. And then in the bottom, I said they're 1.5 meters apart. Squared. Okay. So you do all that, and you get 44 times 10 to the 23rd newtons. 44 times 10 to the 23rd newtons. So Feynman has made his point. That is a pretty big force. Okay, so if you just had 1% extra electrons, you couldn't go near anybody because you have such a big force. However, let's see if it really is effectively the force of the mass of the Earth. Now that whole question doesn't make sense because you need the Earth to generate the gravitational force. So let's not worry about that. Let's just set this equal to mg and see what is effectively the mass it would take to create this force. That's really what he meant. And you can see, you know, G is more or less 10. So it's going to be roughly, the mass that we're calculating is going to be about 4.4 times 10 to the 23rd kilograms. So I just divided basically by 10, put the decimal point there. Well, the mass of the Earth is 6 times 10 to the 24 kilograms. So, I'll never get to say this again, Feynman was wrong, right? It looks like it's actually not quite that big, okay? However, I'm not allowed to conclude that Feynman was wrong. That obviously would be very unwise. So really, though, it depends on all these numbers. You can see formulas are often very sensitive to little parameters that you put in. For example, if we made them weigh a little bit more, that would be more charge. And you might say, well, maybe a little bit more, but it's squared, right? So if we made them weigh 2 times more, it would be 4 times higher, right? And also the separation is also squared, also very sensitive. Maybe when he said arm's length, he meant they were like, you know, hugging. Because you make them twice as close, and then again, it goes up by 4. So it doesn't take much to get you from 4.4 to essentially, or 0.44 to 6. It just depends on really how you estimate the numbers. The point really is that it's a very, very large force. Electrostatic forces are very big, and coulombs are a lot of charge.